High-precision model scanning with photogrammetry can generate gigantic 3D meshes, containing more than 200 million vertices. Viewing these models on the web with high fidelity is beneficial for the fields of cultural heritage and maintenance. We introduce a framework built around an existing progressive compression and decompression algorithm to process these meshes and view them online. Our goal is to efficiently transfer them and adapt the decompression to the view and device performance. Our framework can be separated in three major stages. A gigantic triangle mesh is first pre-processed on the server, then transferred with our compact representation, and is finally reconstructed on the web browser. Due to its size, we start by partitioning the original gigantic 3D mesh out of core on the server. We recursively process the resulting submeshes by compressing them with the topology encoding decimation conquest, and then stitching them 2 by 2 with their neighbor. This creates a binary tree of compressing plus stitching operations. The final remaining mesh is the base mesh and corresponds to the coarse representation of the complete model. At the end of the preprocessing step, we obtain global and local information. The global information includes the base mesh and the tree structure, with a bounding volume and quality criterion per node. This is downloaded only once when we start the runtime process. The local information contains the decompression and separation properties, linked to each node of the graph. This will be downloaded based on the selection at runtime, and only once per node. Our framework is separated into two runtime processes. The first one interprets the tree as a multi-resolution representation of the mesh. It selects for every frame the optimal nodes based on visibility, mesh quality, and device performance. The second one uses the tree as a decompression dependency graph. Starting from the base mesh, it downloads, progressively decompresses, and separates the nodes to reach the optimal selection. Only targeted nodes are downloaded and decompressed. Each reconstructed node is saved locally to render in WebGL and can be reused when the optimal view changes. The progressive decompression allows us to see the model even if not fully decompressed, and the mesh gets refined over time. Previous multi-resolution approaches required that each submesh was encoded and downloaded individually. Our representation is more compact, a base mesh and the steps to refine it progressively. Each submesh is defined implicitly from the decompression and separation of its parent mesh. Thanks to the view-dependent tree traversal, this framework lets us view the original details of gigantic meshes on the web.